Nikhil Mehta and Pedram Pejman. Today, we'll be previewing a new open source Python library called NitroML, Accelerate AutoML Research. The goal of this project is for you, the AutoML researcher, to BYO AutoML on TFX and KubeFlow. For those of you who aren't familiar with these technologies, I will cover TFX and KubeFlow in the demo. And by BYO, what we mean is benchmark your own AutoML. Regarding Q&A, I would like to save that for the end of the presentation. Feel free to post your questions in the chat on the upper right-hand side of this Google Meet, and we will address the questions at the end of the talk. Now, before I begin, let me just introduce you briefly to our AutoML research team in Google Research. The work that I'm about to present incorporates the accumulated knowledge of our team building AutoML systems in production, as well as developing new algorithms for AutoML used in real Google products. This work couldn't have been done without the many contributions of AI residents, engineering residents, and research interns who have joined us on rotations over the years. And if you are interested in opportunities, you can visit this link here at the bottom of the slide. This link will again be posted in the chat, and we'll have it at the end of the talk as well. To summarize the talk, NitroML is a novel framework for AutoML researchers that offers access to standard AutoML benchmark datasets and tasks. It implements benchmarking best practices. NitroML accelerates AutoML research with built-in AutoML components to find your own pipelines. And it leverages two open source libraries, TFX for ML pipeline expression and KubeFlow for execution. I'll cover that more throughout this talk. But using these two technologies, we're able to scale our AutoML benchmarking with cloud compute on Google Cloud. Now, NitroML is currently closed source, but we're looking to open source it to GitHub in Q4 of 2020. So what is end-to-end AutoML exactly? The way we're going to define it is as a machine learning pipeline that produces high-quality models for novel data sets with minimal human intervention. So on one end, we're going to be passing raw data into our AutoML system. And at the other end, we're going to export models and evaluations. Now, under the hood of this AutoML system, we generally have multiple AutoML sub-modules or phases. This diagram was taken from this Google AI blog post titled End-to-End AutoML Solutions for Tabular Data at Kaggle Days, which was posted by a Google research team who had participated in a Kaggle competition, and their AutoML system came in second place, beating over 80 teams in an AutoML competition. The pipeline that they used looked roughly like the following, where the dataset came in and passed through multiple phases of AutoML, including automated feature engineering, automated architecture search, automated hyperparameter tuning, model selection, automated model ensembling or selection of the best model, and then finally, automated model distillation and export for serving. Now, the motivation and research challenges that pushed us to develop this new framework were the following three items. First of all, the need for better AutoML benchmarking was identified as the biggest challenge at the ICML 2019 AutoML workshop. Second of all, there's an extremely high upfront engineering cost required to do end-to-end AutoML research. As you saw above, in order to build a competitive AutoML pipeline, you need these multiple stages that perform AutoML on their own. And we asked ourselves, how can we lower the barrier to entry so that new incoming AutoML researchers can participate in AutoML research? And finally, we needed to develop a framework that could support heterogeneous multi-stage AutoML. What we mean by heterogeneous are pipelines where each stage could have a very different footprint. For example, consider the following pipeline where we have three stages. In the first stage, we perform distributed data processing. So we launch a job that will distribute data preprocessing across a cluster of commodity CPU machines. And next, we would like to tune several neural networks on TPUs on the pre-processed data. So now we're talking about a machine that has access to an accelerator. And lastly, we want to take the best K models and ensemble them on CPU. Before I dive more into NitroML, I would like to mention some related work. The de facto AutoML benchmarking framework today is OpenML.org's AutoML benchmark, which is open source at github.com/OpenML/AutoML benchmark. And this system allows anyone to benchmark open source AutoML systems. And they've already integrated several open source AutoML systems and have benchmarked them on OpenML datasets. The other two related works that we're going to mention aren't benchmark systems per se, but they're competitions used for AutoML. Specifically, ChawLearn and AutoML.ai have been hosting AutoML competitions like the AutoDL Challenge. And it's worth mentioning them because competitions push AutoML research quite heavily. And they're not that conceptually different than a benchmarking framework because many of them under the hood use something that allows you to execute your AutoML system. Most of these competitions are organized on top of an open source framework called CodaLab for organizing competitions. And lastly, it's worth mentioning Kaggle because while historically Kaggle was used for data scientists to compete on real industry data sets, lately, they've updated their terms of service to support AutoML systems participating in ongoing competitions. And one example of that was the competition mentioned earlier. An example of good AutoML research requires benchmarking on many data sets. So we need to have access to 5 to hundreds of data sets. When we're doing AutoML on image tasks, there's fewer canonical data sets. So performing well on multiple of them is already sufficiently good. But when we're talking about end-to-end tabular AutoML, where there's a significant variance in the types of data sets you can see, it's worth benchmarking on hundreds of them to really understand how your AutoML system's performing. We would ideally like these data sets to be of various sizes, meaning number of rows or columns, but also the kind of tasks that we're addressing, such as classification, regression, or even multitask. We'd also like, ideally, to compare multiple ML frameworks. We would ideally like to have a benchmark system that can support TensorFlow, sklearn, PyTorch, and even AutoML systems that aren't implemented in Python. And in order to benchmark or do AutoML research, you need lots of compute. Most of the best AutoML papers have used thousands of CPU hours, and they've even used accelerators to help accelerate the production of their experiments for research papers. Because many of the times they need to benchmark on hundreds of data sets and train dozens or hundreds of models on these data sets. And finally, what makes good AutoML research, or what makes a good AutoML pipeline, is one that does well on average, not just on a single data set. As you iterate on a data set, it's easy to acquire domain knowledge and then embed that into your data set. But what makes an AutoML system special is that it's able to do well given an unseen novel data set. An example of a very good AutoML benchmark comes from this recently published paper, AutoGlue on Tabular, which I pulled from arXiv. And this screenshot shows how they benchmarked their system, AutoGluon, which is an open source framework from Amazon, against 5 other popular AutoML systems. On the left-hand side, they show how their system performs on over 30 OpenML benchmarks that have become standard for AutoML benchmarking. And what they show here is the relative performance of their framework versus the others on these data sets. And so we can see how their framework performs on average across these data sets. On the right-hand side, we see their benchmark against a different set of data sets. This time, they're from Kaggle. And so here we have a dozen Kaggle data sets from real competitions where data scientists had participated in the past. All these competitions are over, but what they report on the x-axis here is their percentile rank on the leaderboard, meaning that in a couple of these data sets, for example, this one and this one, AutoGluon outperformed 95% of data scientists on this particular data set. So as you can see, there's some challenges inherent to benchmarking AutoML because data sets come from different sources, and there's different ways of measuring how you perform. You either need to compare yourself against other AutoML frameworks, but you also need to compare yourself against real human data scientists. With that, I would like to introduce you to our framework, NitroML. NitroML is a Python framework that empowers AutoML research teams to quickly build and iterate on scalable, multi-stage AutoML pipelines. And we do so in a repeatable and data-driven manner through benchmarking. So fundamentally, benchmarking is at the core of the NitroML framework. And that's what allows us to be data-driven as we iterate on model quality and build out our systems. And throughout the talk, we'll be talking about AutoML pipelines looking like something like this, with this directed acyclic graph structure. I won't dive too much into this now, but I'll get into that shortly. The workflow as the AutoML researcher looks like the following. So here's you, the human in the loop. And there are 4 phases in the AutoML lifecycle using NitroML. First of all, you define your AutoML pipelines and benchmarks in Python. And we use the TFX library under the hood to define and express the pipeline that you're going to want to execute. The second phase is to compile and execute that pipeline that we defined on the cloud at scale. And we're going to use a technology called KubeFlow, which is also open source. And this is what powers the orchestration. The orchestrator is going to execute our pipelines with a directed acyclic graph that looks like the following. And as the various stages in our pipelines complete, artifacts and benchmark results will be written out to a persistent data store that is powered by another open source technology called MLMD, which stands for Machine Learning Metadata. And finally, we can analyze the results in a Jupyter or Colab notebook when we're inspecting how our pipelines performed on our benchmark data sets. And once you have those results, you can iterate on your pipeline. Here's an example snippet of what the code looks like. And this is a fully working example for NitroML. So first of all, we're going to create a Python script. Here we called it myAutoML on OpenML benchmark.py. And all we need to do is import NitroML. This is the framework we're discussing. And we use NitroML to benchmark our AutoML. We're also going to import a module called myAutoML, which is going to define a class which will build our actual pipeline. The way we define a benchmark in NitroML is conceptually very similar testing to how you would write a unit test in Python. And that was something we kind of wanted to build in from the start, is get you familiar with designing your benchmarks around the idea of like tests for machine learning. So we'll define myAutoML benchmark as a subclass of NitroML.benchmark. And we're going to benchmark our AutoML system on 3 tabular tasks. All we need to do is override this one method called benchmark. And then we'll iterate over this list of task names, which include common tasks, which are the adult data set, CFAR10, and the diabetes data sets. For each one of these tasks, we're going to define something called a sub-benchmark. And a sub-benchmark allows us to easily reference the benchmark that we're defining programmatically and on the fly at analysis time. So for example, if we look at the sub-benchmark for CFAR10, it's going to be called myAutoML benchmark.cfar10 in the analysis Colab. Within this for loop and within this context of sub-benchmark, we're going to create our task. So we're going to call this, we're going to use the built-in OpenML task fetcher that comes built into NitroML, and that's going to fetch the task by name. Next, we're going to create our AutoML pipeline by passing in the task as well as the train examples that it should use. And finally, we're going to call self.evaluate, which is the only method you need to call within the benchmark. And that's going to take 3 arguments. It's going to be pipeline that we want to execute. And that's going to be obtained by calling my AutoML.pipeline. We also want to pass in the model that we want to evaluate. So that we're just going to call my AutoML model, which is going to return the best model. And finally, we need to pass in the examples to evaluate on the test examples. And finally, one second. Finally, down here in our main function, we're just going to call NitroML.main to kick off our benchmark. My AutoML is a simple class that does three things. First of all, it's going to, in the constructor, we're going to take in the task and examples, and we're going to use the task to define how to build our pipeline. And our pipeline is going to be composed of TFX components. So we're going to use this built-in component called TFX transform, which will pre-process our features. We're going to use the TFX tuner, which is going to tune model hyperparameters with TFX tuner, taking in the examples and the transform graph output from the TensorFlow transform component. We're then going to take the best model from our tuner and pass it into our TFX trainer, passing the H params like so. And these components are going to be stored as properties. When we call AutoML.model, we're going to return the trainer's output model. And when we call pipeline, we're going to return the list of the components that compose our pipeline. And this is a full end-to-end NitroML system. Just to give you a bit of an overview of what TFX is, because it is a foundational piece of technology that NitroML is built upon. TFX is used primarily for defining the AutoML DAG. This is a screenshot that we took from the TFX open source documentation. What TFX does is it allows us to express machine learning pipelines as a directed acyclic graph. Where on the left-hand side, we're inputting our data, and we're passing it through multiple components or stages. Each one of these components is going to compute a batch computation. So they're going to do something like transform. For example, this example-gen component will take in the raw data and convert it into a standard format for downstream components to consume. This standard format is going to be TensorFlow examples. And you can see the dependency between these various stages based off the edges that connect them. The edges themselves are what we call artifacts. And these are going to be outputs from our batch processes that are going to be written out to disk. And in order for us to find them, we have a data store that underlies the whole thing that points to all of the artifacts and each version of those artifacts. TFX also provides several out-of-the-box components which are very handy for AutoML. Things like TensorFlow transform, which we use for our feature preprocessing, or tuner, which is used to power our hyperparameter tuning. And finally, we also use the evaluator, which is built off of TensorFlow model analysis. And this is baked into NitroML. So every time you call self.evaluate, it's going to append an evaluator component. And to quickly summarize in 60 seconds, TFX is available on TensorFlow/TFX on GitHub. It allows us to express our ML pipeline as a directed acyclic graph. For some terminology, what we call nodes we call them components, and these perform batch computation. Edges are artifacts, and these are persisted on disk. And with TFX, we get for free predefined components for common ML operations, a flexible API for defining custom components, which is going to be particularly important for us as researchers since we'll be implementing our new algorithms and writing the majority of our Python code within these custom components. And we also get the DAG topology, which is going to be orchestrator agnostic. So baked into TensorFlow extended, or with TFX, we get support for many execution engines, including KubeFlow, which we use primarily in NitroML for scaling on the cloud. But also we support Apache Airflow and Apache Beam. Beam is used primarily for executing these pipelines locally on our machines during development, so that we don't have to wait for the overhead of our cluster scheduling the jobs. Once we've defined our pipeline DAG, KubeFlow is going to provide the orchestration and UI in this demo. So here we have the actual pipeline that was produced from that NitroML benchmark script I showed you above. So here we have 3 sub-pipelines that are composing our overall pipeline. And we have one pipeline for each one of the tasks that we're addressing. And my AutoML, that class under the hood, was creating multiple components, which are expanded out into this DAG. What we call each one of these sub-pipelines is what we're going to refer to as a sub-benchmark. Once those executions are finished, we can inspect all the results as pandas data frames inside of Jupyter or Colab. For example, here we can see a table with execution from a different run where we ran our AutoML pipeline on many of the OpenML datasets. So these are all datasets taken directly fetched from openml.org. And our pipelines, we can see the performance metrics on them, such as average loss, accuracy. And on binary classification, we even get AUC and AUC precision recall out of the box. Let me hop to a live demo. OK, so the first thing I'd like to show you is a real Python script for an OpenML benchmark that executes a AutoML pipeline on 72 datasets using NitroML. So all we need to do within our OpenML cc18 benchmark.py file is import NitroML and import TFX. NitroML is going to be the benchmark, the language we'll use to define a benchmark, and TFX will be the language we use to define our pipeline. We then create a class OpenML cc benchmark, which inherits from NitroML benchmark. And within the benchmark method, we're going to iterate over we're going to obtain the list of datasets from the built-in NitroML OpenML cc18 fetcher. And we will iterate over that list of datasets, create a sub-benchmark per task, and then we're going to create our AutoML pipeline. So here we're going to use several TFX components, such as StatsGen, SchemaGen, form, and our trainer. Once we've created those components, we're going to gather them all in a pipeline list, like so. And we're going to call self.evaluate with that pipeline, passing in the examples that we're going to use for evaluation and the trainer's best model. And finally, inside of the main function, we're going to have 2 options. Either we can execute our pipeline using KubeFlow, in which case we call NitroML main with the KubeFlow DAG runner, which is built into TFX. Or alternatively, if we're iterating on our pipeline and don't want to wait for our jobs to schedule on cloud, we can just run it locally using Apache Beam on our local workstation. The resulting pipeline looks like the following. So here I'm in the KubeFlow UI. And here we see each of the sub-benchmarks we define for the OpenML tasks. So for example, this one here is this node here is the example gen for the dresses sales benchmark from OpenML. This is for the credit approval benchmark. This is for the DNA benchmark, and so on. And I think in this example, we have 72 pipelines. There's several benefits to having an orchestrator backing the benchmark execution. One of them is that we can see how our stages are executing over time and can see which ones are succeeding, which are failing. For example, here, we say that there was a failure during the data preprocessing step on DNA. And if I click on it, I can see immediately what the error was. OK, so the error at this stage is that we ran out of memory. And this is going to be fairly common with heterogeneous pipelines, where different stages have different footprints. And so what we'd ideally want is to use a container that has access to more memory for the transform stage. But we can also view the log. We can also hop to the logs if we'd like for the particular stage. Because these pipelines can be fairly long running, especially on larger data sets, if we're operating on terabytes of data, these initial tasks, these initial stages in our pipeline can take several hours to complete. and they can produce lots and lots of logs. And so if we just want to inspect the logs from our trainer component, we can just hop to the logs pane right here and view the logs inside of Stackdriver. Maybe that will load. And lastly, another benefit of using an orchestrator and this DAG abstraction is that the orchestrator is able to manage schedule execution of these stages and maximize parallelization and utilization of the available cluster. Because we're executing all of this on the cloud, we pre-allocated a cluster of machines, and the orchestrator will assign work to those machines as as stages are able to execute in parallel. And finally, once we have those benchmarks executed, we can hop to our friendly little Colab notebook. This is a built-in notebook that comes with NitroML, and you can, of course, extend it to your heart's content. All we're going to do is import NitroML and a couple of the definitions for importing our data store. We first need to connect to our data store, which is going to be, again, MLMD, the open source software I mentioned earlier. MLMD can have multiple data stores backing it, such as SQLite or MySQL, or even a managed data store that's built into Cloud AI Platform. Once we're connected, we can just load up all of our benchmarks. Here's some benchmark runs I ran earlier. These are for a couple. Here we see results for a couple OpenML datasets, in particular the climate model simulation crashes and the vowel dataset. Next to these benchmarks, we can see the hyperparameters that we used for our trainer. We can see the performance on those benchmarks for these different benchmarks. And we can also do things like run multiple runs of the same benchmark. So for example, here I had ran the OpenML climate benchmark 5 times. And we can see for each one of the runs the performance. And we can also use these runs to aggregate our results and compute error bars and means for our metrics. And this is especially important inside of AutoML, where there are many sources of randomness. And because there's so much search involved, in particular in things like the tuning stage of our pipeline, we can see an extremely high variance across performance of runs, which is why it's so important to have multiple runs for AutoML systems. I mean, just here we can see that the accuracy ranges from 14% through 37% for the same exact pipeline and hyperparameters. Now I'll hop back to the demo, to the presentation. So now that I've discussed how NitroML leverages benchmarking, now I'd like to discuss a little bit more on how NitroML helps accelerate AutoML research. So for researchers, NitroML provides the following 3 additional features. One is that it gives you easy access to standard AutoML datasets. 2, artifact sharing is possible with sub-benchmarks, which allows you to iterate more quickly on your pipelines, especially when dealing with large datasets. And 3, NitroML provides out-of-the-box AutoML components that you can use or extend when doing your own AutoML research. Regarding the standard AutoML datasets, NitroML fetches its AutoML benchmark datasets directly from 3 data sources at the moment. The first is TensorFlow datasets, which includes many standard datasets used in TensorFlow research, so usually deep learning. And these are usually going to be datasets like image datasets, language, speech, video, and then there's a few tabular datasets included there, but not too many. OpenML.org, on the other hand, has many, like thousands of tabular datasets that are very good for using in AutoML research. And they also include the AutoML standard benchmark suite of this that they include in their benchmark framework. And lastly, as we saw with the AutoGluon paper, Kaggle datasets are becoming quite important in AutoML research for comparing performance against other baseline systems. And so we also fetch datasets directly from competitions there, so that you have a single place that you can define your benchmarks and have easy access to all these data sets. Now, a nice little component or feature built into NitroML is these sub-benchmarks. These sub-benchmarks can be used to define splits in your pipeline so that you can share artifacts with downstream phases and components. And this allows us to do easy ablation studies in our complex workflows, which is particularly important when doing research in AutoML systems where there's so many stages that could contribute to the final performance of the pipeline on the data set. Here's a concrete example. So we're going to create a benchmark called myTrainerBenchmark. Again, subclassing NitroML.benchmark. This time we're going to fetch a single data set from OpenML called the diabetes data set. And we're going to create a stage here called TF transform, which is going to pre-process our features. But if we have an extremely large data set, like perhaps imagine like a terabyte of data, this computation can be very expensive because it needs to do a full pass over the whole data set, and we might need to distribute the computation on the cloud. Now imagine that we want to explore the effects of changing the learning rates on our trainer component. So what we can do is we can iterate over a list of learning rates, as chosen here, and we're going to create a sub-benchmark for each one of those learning rates. Each one of those sub-benchmarks will have a name, something like myTrainerBenchmark.learning rate equals the actual value. Then we can pass that learning rate to the instance of the trainer we're creating in that sub-benchmark. And we can pass that to the evaluate function, just passing the trainer component itself. The resulting DAG will look like the following. Will look like, oh, it looks like I lost it. All right, here's what it looks like. The resulting DAG is going to look like the following, where the upstream stages of our transform will all be shared with these downstream splits. So here we have our trainer using learning rate 0.0001, and this is our trainer using learning rate 001. And for each one of those trainers, we're going to append an evaluator component, and each of these sub-benchmarks will get its own row in our Colab Notebooks pandas data frame. And lastly, NitroML provides some out-of-the-box AutoML components. Two of them that we'll mention are AutoData, which conveniently automates feature preprocessing, engineering, and selection for downstream trainers and tuners. This is useful when benchmarking different trainers, or if you're like most researchers who are interested in just iterating on the actual model itself and not so much the feature preprocessing. This is an extremely useful tool for getting you started and having a single input vector for all of these different data sets that we support. We also provide a auto trainer component, which is useful for those researchers out there who are interested in iterating on different feature engineering or preprocessing mechanisms. This auto trainer can tune its own hyperparameters, so it can do a hyperparameter search, and it provides a base class that you can subclass when exploring your own models. Here's how we use AutoData. So this is taking the exact same script that we saw earlier. The only difference is that we replace our transform stage with NitroML.AutoData.AutoData, which only needs to take in the examples, so the tasks training examples. We're then going to pass the transformed examples that were created by AutoData to our trainer. And we just need to make sure to pass the AutoData components and append that to the trainer components when creating our pipeline. A couple additional features worth mentioning are that NitroML supports benchmarking different task types, such as classification, multitask, and regression. These come out of the box. NitroML offers easy debugging using two things. One of them is that it's very easy to filter sub-benchmarks by using a regex and a flag. So imagine you have a benchmark script that has tons and tons of nested sub-benchmarks. We can just filter the ones that we want to execute. So the particular path down that graph using a regular expression. We can also use Colab and TensorBoard to dive into the specific runs when you're using a model that supports TensorBoard integration. NitroML also has built-in support for error bar computation by setting the runs per benchmark equals n flag. And we can leverage the benchmark result data store to monitor model quality changes over time per benchmark. And we can see this concretely here in this screenshot. This is taken from a real attempt at us participating in a Kaggle competition where we were iterating on model quality for our AutoML system. And on the x-axis, we have time. And on the y-axis, we have RMSE. So lower is better. This is the metric that we were optimizing for. We ran our benchmark several times while we were changing certain snippets of code in them. And we didn't see that much of an effect on model quality. We can see that the error bars have a significant amount of overlap. And so none of the changes were really that significant. Until here, where we introduced an improved tuning search space. And we can see that the improvement was drastic, where we see a significant change in the actual RMSE value, and we don't have any overlap in our error bars. And all of this came for free when using NitroML. In conclusion, NitroML is a novel framework for AutoML researchers. It offers access to standard AutoML benchmarks, datasets, and tasks. It implements benchmarking best practices. It accelerates AutoML research with built-in AutoML components to define your own pipelines. And it leverages the open source libraries TFX for ML pipeline expression, KubeFlow for execution, and MLMD for storage. We didn't cover MLMD too much, but keep in mind that it is the data store that backs all of NitroML. And using all of this, we're able to scale well with cloud resources on GCP. And once again, we're expecting to come to GitHub by Q4 2020. And lastly, I'd like to mention the roadmap for NitroML. We would like to integrate several baselines, end-to-end AutoML systems as components into NitroML. So we would like to make it very easy for you to benchmark your own AutoML pipelines against baselines like Cloud AutoML Tables, AutoSKLearn, and AutoGluon, which were included in that example I showed you earlier from the AutoGluon paper. And perhaps we can leverage the OpenML framework, AutoML framework, benchmark framework, which came out last year to do so. We would also like to fetch more datasets from other repositories. So we'd like to fetch more datasets from openml.org and Kaggle. But we'd also like to fetch them from the competition sites, chalearn.org and automl.ai.org, automl.ai, which organize the AutoDL challenge. We're also building out a Kaggle API integration, which allows us to automatically submit model benchmark results against the Kaggle leaderboard so that we can store your Kaggle leaderboard ranking relative to other participants inside of, and analyze that in the Colab notebook. And last but not least, we would like to provide more AutoML components for researchers to combine and extend. Our AutoML research team at Google is developing many exciting algorithms, many of which aren't yet open source, but we're hoping to publish them. And NitroML will help us get there. With that, I'd like to thank you for your time. Again, if you're interested in collaborating, please reach out to Pedram at peddy@google.com or me, Weil@google.com. I would like to open the floor for Q&A. And if you have any questions or interest in interning or coming to work for Google Research, please visit this link down here. So for Q&A, I'd like to hand it to Pedram, who I assume dialed into the call, who will be moderating the Q&A.
Hey, Charles. Yeah, so hello, everyone. I'm Pedram. And so first of all, thank you guys for coming, and I hope you enjoyed that. Please take a second to either sort of unmute yourself and just ask any questions or thoughts that you've had over the course of the presentation, or if you can't sort of verbally talk about your questions, please utilize the chat at the top right corner of the Google Meet page. So I'll just sort of pause for 10-15 seconds to see if anyone has any thoughts or comments.
Yeah, I had a question, Charles and Paddy. I wonder if it's worth expanding whether the caching capabilities are very useful or not in the AutoML setting. So the ability to kind of resume computation from the middle. And if you could elaborate on this.
Yeah. Okay. So regarding caching, and this actually was a big motivator why we decided to frame our AutoML system as these pipelines, and why we decided to build on top of this pipeline abstraction. So one of the benefits of programmatically defining a pipeline like this is that you can perform partial executions. So the first time you execute your pipeline, you're going to want to run it end to end. But as those artifacts are computed, in particular commonly we see that we want to cache the data pre-processing step, because this can be fairly expensive, and most researchers will do it once and then kind of use those results fixed as they iterate on their trainer or their hyperparameter tuner search space. So using this pipeline abstraction, we're able to easily define a way to both cache the artifacts produced by these components, and we're also able to express a way for partial execution of our pipeline by essentially programmatically restructuring the DAG to use the artifacts pre-computed and execute them. So that's a huge benefit of using this pipeline architecture. If you were to do this in your own Python code, there'd be a good amount of work in having flags to check that the results are there or not. And that's something we get for free from TFX. And it's easy to get wrong.
Do we have any telemetry of how frequently this is used? Or do we know how frequently people run those AutoML pipelines end-to-end versus kind of from the middle, as you kind of explained?
Yeah, so I can comment on that, where as an AutoML researcher, I frequently run it from the middle, or at least I want to. To tell you the truth, we're still developing how we're doing the exact partial run implementation, but that's on the roadmap. And this is the #1 feature requests that I've gotten from other researchers when running on pipelines, where they're saying, okay, it's really nice that we get the raw data in the beginning, but we also want to resume computation from the middle. And so this is something that we're already exploring and are beginning designs for handling that.
Okay, thanks.
Mm-hmm.
Yeah, please just unmute yourself and ask a question if you have one, Matthias.
Hey, thanks, Charles, for the presentation. I'm having 2 questions. First, could you elaborate a bit more on what these functions are, or will this be documented openly, what these components are that you give there?
Mm-hmm. So actually, in this example, all these components are publicly available at TFX on GitHub. If you just Google search TFX GitHub, you can see all the components are available here in this repository. So in the examples that we're showing, we're not actually using any particular AutoML components. Part of what we're doing with NitroML is allowing you to bring your own pipelines that you defined with TFX for AutoML and allow you to expand them into AutoML systems that can operate successfully on many, many data sets and allow you to iterate very quickly. There is ongoing work to actually create our own custom components like auto data and auto trainer, which will come built into NitroML. But if you want to explore more about the components that are available, you can visit this repo here. And it's actually under the components directory. You can see all of the built-in ones, like the tuner component, which uses Keras tuner. Tuner component uses Keras tuner. Transform uses TF transform. Trainer supports TensorFlow estimator and Keras.
Yeah, and just to sort of add a little bit of color, and I see Robert actually also mentioned it in the chat. If you would like, there's also tutorials and sort of higher level guides on TensorFlow.org. And so please feel free to check out the guide and documentation there as well.
Okay, thanks. And the second question I am having is also related to the OpenML AutoML benchmark. So you're both running on Docker, and some people who are doing AutoML research might not have access to a cluster running on Docker, or they might not be able to run Docker at all. Will you have anything or any other mode of deploying this except for Docker? Or are you planning something else?
So, okay, I can answer that partially, which is that if you don't have access to KubeFlow, you can execute the whole thing locally on your machine using Beam, Apache Beam. And Apache Beam is an open source orchestrator, and it doesn't require a cluster. And you unfortunately won't have this nice UI, but you can actually execute your pipelines and iterate on them. And that's what we use for development as we're iterating on our actual code. We haven't really considered any other ways of executing it apart from KubeFlow. Do you have any suggestions or alternatives to Docker?
So I have access to Singularity, which seems to be a prominent alternative with university clusters. And there appears to be an extension for KubeFlow-like extensions to Singularity, but that will, again, then requires asking the admins to install yet another thing, which they sometimes might be hesitant to do.
Yeah, so I don't think TFX currently supports Singularity, but one of the benefits of us building on top of TFX is that it's this layer of abstraction that allows us to abstract away the underlying orchestrator. So if you have something similar to that, it wouldn't be unreasonable to develop your own runtime for example, Singularity that would be responsible for executing the graph. TFX has some very nice semantics for defining what the runner needs to implement. And then you can basically have a portable AutoML system where it can run locally or on KubeFlow or hopefully in the future on Singularity.
Okay, thanks a lot for answering questions.
Yeah, thank you. Great question.
Any other questions?
Also, feel free to ask questions about working at Google. Since this is a demo for a broad audience, and you may have questions, feel free to send them our way.
Hi, could you talk a little bit more about the pre-processing that you're doing in Transform and how you manage that for the different data sets that you're looking at?
Okay, sure. So for Transform, we have a built-in AutoData module that I described earlier. And AutoData actually encompasses this subdag here, which is going to be the StatsGen, SchemaGen, and Transform. The benefit of the statistics gen and schema gen components is that given a novel data set, they're able to automatically infer the columns, the column types, as well as any kind of statistics you would need for doing common transformations like z-score normalization of your numeric features or computing vocabularies for your categorical features. And then Transform will give you, with just a couple lines of code, little snippets that will transform the raw examples into tensors that your model can consume within the computation graph. So the benefit of transform is that you're able to do this batch pre-processing during training, and then inference in streaming mode when you're computing an evaluation or doing predictions on your model. So this way, you don't have to manually transform your examples from raw data when passing them into your model. So to answer your question about what the different kind of transformations are, those are going to be those basic ones I mentioned, which are like one-hot encoding for tree-based models or linear models, or they're going to be outputting and embedding for neural networks. Numeric features will generally just be z-score normalized, so that they're normalized between 0 and 1. But we might also do something like some smart bucketization. And this is by no means the limits of what we can do here. A big reason why we're building this on top of a benchmark framework is we want to be data-driven in how we decide which new pre-processing to include by default, or which to include in our search space.
Great, thanks.
Mm-hmm.
All right, we have a few more minutes, so give folks 30 seconds or so to unmute and ask any other questions. All right, so if there are no other questions, thank you everyone for coming. Please see Jackie's comment in the chat regarding the next talk that you can attend. And please do reach out to either Charles or myself if you're interested in collaboration or just interested in this technology. Thank you everyone, have a good day.
Thanks everyone. Thanks, Pedram. See you everyone.